Welcome to this explainer. Today we are getting completely hands-on to understand electrical engineering's two absolutely most important rules, Kirchhoff's current law and Kirchhoff's voltage law, or as you'll usually hear them called in the field, KCL and KVL. Now, if you've ever stared at a glowing, tangled electrical circuit and felt totally lost, well, I have some great news for you. After we walk through these two fundamental laws today, solving those intimidating circuit problems is going to become incredibly easy.
Seriously, just think about that for a second. Want to make solving complex circuit problems feel incredibly easy? I know, it kind of sounds a bit too good to be true, right? But mastering just these two foundational rules acts like a master key. Once you really grasp KCL and KVL, you unlock the ability to systematically break down and solve literally almost any circuit problem placed in front of you.
So here is our quick roadmap. We'll kick things off with circuit problems made easy, move right into KCL and the junction rule, do some calculating, then flip over to KVL, the closed loop rule, calculate some voltage, and finally, stack KCL versus KVL side by side to lock it all in. Let's dive right in.
All right, starting off with KCL, the junction rule. This is where we actually start tracking the flow.
The core idea here is beautifully simple. KCL stands for Kirchhoff's current law, and it means that at any junction in a circuit, the total amount of incoming current must exactly equal the total amount of outgoing current. Think of a junction literally like a super busy highway intersection. Whatever cars drive into that intersection, well, they've got to drive out, right? In our glowing electric circuits, current flows in, and it absolutely must flow out. Zero loss whatsoever. So mathematically, the formula is strictly about conservation. Incoming current equals outgoing current. It's a perfectly balanced scale. There's no magic here, just a strict rule of conservation. What goes in, comes out.
Let's move to calculating current with KCL. Theory is great, but let's actually see this in action.
Okay, picture a junction where we have current arriving from two different wires. From wire 1, we have 2 amps entering, and from wire 2, we have 3 amps entering. Step 1 is to just calculate that total incoming current. 2 plus 3, that equals 5 amps of total incoming current. Easy enough. Now for step 2, we look at the other side of the junction. We know 4 amps are leaving through one wire, but there's a second wire leaving the junction with an unknown current, which we'll just call X. So we set up our really simple equation. The outgoing 4 amps plus X must perfectly equal our total incoming 5 amps.
So here is a quick puzzle for you. Take a second and do the math in your head. If 5 amps go in, and 4 amps are already accounted for on the way out, what is the value of that missing outgoing current X?
You guessed it. The answer is 1 amp. 4 plus 1 is 5. The junction is perfectly balanced. Congratulations, you just successfully used Kirchhoff's current law to solve a problem. See? Incredibly easy.
Shifting gears now to KVL, the closed loop rule. We've mastered current, so now it's time for voltage.
KVL stands for Kirchhoff's voltage law. According to this rule, in any completely closed loop within a circuit, the sum of the total voltage rise and the total voltage drop is always exactly 0. You'll often see this represented mathematically as sigma V equals 0. The absolute key phrase to remember here is closed loop. You start at one point, go all the way around the circuit, and land right back where you started. Whatever voltage gets pushed into that loop, say by a battery, has to be completely used up or dropped by the components like resistors in that exact same loop.
Let's jump into calculating voltage with KVL and put this zero-sum rule to the test.
Let's walk through this loop example together step by step. Step 1. Identify our total source voltage. Let's say we've got a 12-volt battery. That is our voltage rise. Now, as we travel around this closed loop, we hit some resistors causing voltage drops. Step 2 is to subtract those known drops. We hit one resistor that drops the voltage by 4 volts and another that drops it by 3 volts. So, 12 minus 4 minus 3 leaves us with 5 volts. But wait, there's a third resistor in our loop with an unknown drop, X. So, for step 3, we set our entire equation to 0 because, remember, closed loop. 12 volts from the battery minus the 4-volt drop minus the 3-volt drop minus our unknown X equals 0. Simply put, 12 minus 7 minus X equals 0.
Puzzle time again. Let's solve this together. If our battery pushes out 12 volts, and we've already burned through 7 volts on those first 2 resistors, what is the missing voltage drop X needed to bring our total loop sum perfectly back down to 0?
Nailed it! The answer is 5 volts. That remaining 5 volts must be dropped by that final resistor to satisfy the closed loop rule. Honestly, it really is that straightforward. You've officially conquered Kirchhoff's voltage law.
Let's bring it all together now with KCL versus KVL compared. It's super important to know not just how they work, but exactly how they differ. Looking at them side by side really helps. With KCL, the current law, we are strictly analyzing a junction, a specific point where wires meet. But with KVL, the voltage law, we're analyzing a closed loop, a complete circular path. KCL is all about balancing the current flowing in and out of a single point. KVL balances the voltage rising and dropping around a continuous circle.
Both KCL and KVL have now become easy. And honestly, they really have. You now have the fundamental tools to look at any complex circuit diagram, find the junctions to track the current, and trace the closed loops to track the voltage. Thanks so much for hanging out with me for this explainer today, but before we wrap up, I want to leave you with one final thought. If these incredibly strict laws of perfect balance govern a tiny battery and a couple of resistors, imagine how they scale up to control the massive electrical grids powering our entire cities. How many junctions and closed loops do you think are perfectly balancing themselves around you right at this very second? Keep exploring, and I'll catch you next time.